Hi, I'm Matt Needham. This is my lecture on thermostats, pressure switches, and other electrical control devices. Let's begin here with the introduction. Really, when you think about the hallmark control of our trade, it's really the thermostat. The thermostat is, we're concerned about humidity, airflow, refrigerant pressures, these things, but really the thing we deal with the most is the air temperature in a room, in a house, inside a refrigerated box, and so the thermostat is like the control for our trade. We're also going to talk about pressure switches and transformers. Now, transformers are used to change one voltage into another voltage, and really in the air conditioning refrigeration industry we're always just dealing with step down transformers, whether it's 4160 volts to 460 volts or 460 volts to 230 volts or 230 to 24 volts or 230 to 115. And usually a lot of times inside air conditioning units, the voltage that we're creating with a transformer is quite commonly your 24 volts, whether it's a package unit that takes 230 volts and drops it down through a transformer to 24 volts, or a split system that takes 115 volts and drops it down to 24 volts. And here we have the electrical symbol for the transformer with a primary and a secondary. And if you're getting voltage in the top, like your primary 230, and you're not getting voltage at the bottom of 24 volts, if there's a reset, you can try your reset on the thermostat. But if there's not, the transformer, not the transformer needs to be replaced. Now, before you replace the transformer, you should check to make sure none of the wires or components in the secondary are grounded or so badly shorted that they'll burn up the new transformer. But that's the operation, is dropping it down generally to 24 volts inside of our units to control things like thermostats and contactor coils, etc. And that's using the voltmeter, but then you can also verify your diagnosis if you think it's a bad transformer by taking the resistance here in the primary, which should be a measurable resistance. It shouldn't be zero, it shouldn't be infinite or a billion ohms. It should be a measurable resistance, 20, 30, or whatever ohms. It could be more or a little bit less. And then some measurable resistance in the secondary. It shouldn't be burned open, be an open lead or infinite. It should be a measurable. And the secondary resistance is going to always be less than the primary because we're stepping down the voltage. Okay, thermostats, generally the basic concept is that we open and close a set of contacts. And for a cooling thermostat, when the contacts close, it's like the thermostat saying, hey, it's too warm in here, we need cooling, let's close and send an electrical signal so that a compressor, a refrigeration compressor, can come on, either directly with a line voltage thermostat or indirectly with a low voltage thermostat and the use of, let's say, a contactor. Now, in a heating thermostat, we're going to talk about, it's like saying it's too cold in a house. We need to close and bring on something to make the room warmer, like a gas valve that can then open up, create a flame, heat up a heat exchanger so that we can heat a room, a house, a zone, what have you. And then when it gets warm enough, the thermostat says, hey, it's warm enough in here, we're going to open up. And thermostats need to be mounted in the area that they're controlling. In a room, cooling thermostats for refrigeration should be mounted in the box, whether it's a refrigerated box or a freezer, so that it accurately senses the temperature that it's trying to control. We have different types of thermostats. Here we have a remote bulb thermostat, where this bulb can be in the refrigerated space, but the actual control thermostat may not have to be. And you can set the temperature of your refrigerated box here, and then a set of contacts open and closes to bring on cooling when the box gets too warm. Let's say the box gets to 41 degrees, the contact closes, the refrigeration compressor comes on, it runs and runs and runs, the temperature in the box drops to 35 degrees, we'll say. The thermostat says, hey, I sense that it's cold enough. Let's open our contacts, and then no electricity flows through the thermostat, and we shut the cooling off. And this happens over and over again so that we maintain a constant temperature in our refrigerated box. Okay, so this is a remote bulb thermostat. A lot of other simple thermostats may work with a bimetal situation, which is brass and steel wound together, and they have different rates of expansion and contraction, which create movement. And in this movement, you can make or break a set of contacts. Here's a kind of a manually operated air conditioning thermostat. Okay. Now, also a little bit, if you want more on this, you can go on YouTube and watch Needham's opposite lecture. It's the title of the video. And one of the points I make on that video, which is a little more complicated lecture than this one, is these two items, the line voltage and low voltage thermostat, show up on my opposite lecture because it's a little opposite of what you think. It's a little counterintuitive. The line voltage or high voltage thermostat is for small air conditioning or refrigeration systems. And that we have a direct thermostat, something that will let the line voltage and higher amperage through it, and this directly line voltage thermostat lets the electricity go through it to directly turn on the compressor. And these are for small systems because the contacts of a thermostat can handle that 3 or 4 amps. But some of the bigger systems that might use a thermostat like I just showed you, like this for air conditioning, that might use 15 amps or so, the little baby contacts in here can't handle that much electricity. So these are low voltage thermostats, and they would control like a contactor, and the contactor would then bring on a air conditioning compressor. So the low voltage thermostat is for larger tonnage equipment, a little opposite of what you think. Now, thermostat installation is pretty simple, just usually a couple of screws. And again, you want to choose a suitable location for a thermostat. You want, generally for a home, you want it to be near the return air, not in a specific one room, but in a common area of the house near the return air, not near a heat source like an appliance, a coffee pot, a window that can let light in to shine directly on the thermostat, or anything like that, because it'll fake the thermostat out. You also, one thing I don't think write enough about is you don't want it to be near any like heavy vibration, like near a door where someone's slamming the door all the time, and that'll cause the thermostat to vibrate, shortening its life. Okay. Okay. Now, this, on troubleshooting thermostats, we talked for a little bit about it. The commentary here is a little bit more about installation. If the thermostat is getting power but not passing it through when it should, then really the thermostat's at fault and it needs to be replaced. If it's getting 24 volts and you have a call for cooling, but it's not letting the 24 volts out, let's say on the Y terminal of an air conditioning thermostat, then we can say that the thermostat itself is not working, and we can replace the thermostat. Likewise with heating, if it's not giving power to the W on a call for heating terminal, then we would think that we probably need to replace that thermostat. On maintenance, things are pretty digital now. Keeping the thermostat just clean, maybe even, you know how you use your air to clean like a circuit board on a computer or something? Getting it in there once in a while and blowing out your thermostat. And you'll see most thermostats are designed with little holes that can allow air to pass through them, so that, because when you mount it on a wall, you want it to take the temperature in the room and let some of the air pass through it. So taking the cover off your thermostat, blowing it out, might not be a bad idea every once in a while. Also making sure that the electrical connections are tight. There's baby little screws in there with tiny little wires, and just torquing those down, making sure those connections are tight is not a bad idea. Okay. Staging thermostats, they can operate different equipment at different times. Quite often, it might be part of a two-stage system where a thermostat is bringing on some cooling, and then if it gets a little warmer in there, it might bring on more cooling or all of the cooling. And then in modern systems, they'll rotate. So if you have a thermostat contact bring on, let's say, compressor number 1, and then it gets a little too warm in there because the compressor number 1's not handling the job, then compressor number 2 comes on. But in modern systems, they want the equipment to wear evenly, so then if a computer's involved or a microprocessor, then the next time the system comes on, compressor 2 would start first, and then compressor number 1 if we had to have full cooling, let's say. Okay, we'll give more on that here in a minute. Okay. Because loads fluctuate a great deal, instead of just giving all cooling or no cooling, we're going to a point now with technology where we'll give you, like we said, some cooling. And there's a lot of disadvantages to turning on a big air conditioning system and then shutting it off, and turning it on and shutting it off. It tends to use a little more electricity. Let's say you have ductwork, the hot air builds up in the ductwork, you then have to blow that hot air out of it and start again. You get this inrush current known as locked rotor amperage when you start up big compressors or whatever. And so it's not a great idea to be having the equipment on and off all the time. It can wear out the equipment and waste some energy. It's nice to allow the equipment maybe to be run at a little bit lower pace for longer periods of time. That'll also maintain a more even temperature instead of a simple thermostat with one set of contacts bringing on the cooling at 74 and shutting it off really at 72. I know that your thermostat is set at 73, but that's really what's happening for a simple system in a house. It might be more like it comes on at 70, it's running more just at 73 and a half and maintaining that with modern technology. Okay. Some scroll compressors on even residential systems with two-stage thermostats can have it run at 2/3 capacity and then at full capacity. It's 2 stages, like the first stage and the second stage, which I'll give you an example of in a minute. Now, on staging thermostats, a lot of times we talked about how the terminal on the thermostat is Y. So here we have cooling thermostat. Let's say the temperature rises up to 73 and comes on, which is Y1. And then if the temperature were to keep rising because that wasn't handling it, and it got to, let's say, 74, then this would close and Y2 would come on, and you bring on full cooling. So if you're a couple degrees above the set point, you get full cooling. If maybe you're only 1 degree above that set point, you might just get half or 2/3 of the cooling. And then this is the Y2 terminal, or the second stage. So you have this even on some more advanced residential systems. And you can look for this 2-stage with the Y1 and the Y2 on your thermostats. And then also we have it similarly for heating, W1 and W2, where actually the flame, the gas valve, will open up partway with W1. And then if you need more heating, the gas valve contact closes for W2, and then the gas valve opens all the way, and the flame, that blue flame, grows a little bit, producing more heat. And there's all kinds of new technology coming out all the time, but I want to give you the basic concepts of how these staging thermostats work. Okay. Now on heat pumps, a heat pump is a way of heating and cooling with just traditional refrigerant, not having natural gas or anything like that in order to heat. And it causes, it's another course, it causes, instead of the refrigerant just going in one direction, compressor, condenser, metering device, evaporator, back to the compressor, and you'll have to watch some other lectures or take some other courses, and I'll really slow it down for you. The refrigerant goes in the opposite direction, and it actually takes some of the heat from outside, even though it's cold, there's some heat out there, intensifies it, and has it go inside by use of the refrigerant flowing in the opposite direction. So we can still on the heat pumps have Y1 and Y2 as you normally would with cooling, but for heating a lot of times you'll have W1, which is traditional refrigerant heating with a heat pump, and then W2 might be electric strip heat in downstream in the supply air, which if it got really cold outside and you don't have enough heat outside to really heat the structure, you bring on some electric heat, which is a little more expensive than running your heat pump per BTU, and you'll add heat that way, supplemental heat, and that might be your W2. Also, because you're running cooling when it's cold outside, you can build ice on your outdoor coil, so we have to kind of go into a defrost cycle, and instead of it flipping back into cooling and blowing cold air on the people, it will do that, but then you turn on those electric heaters to mitigate the cold air so the air comes out neutral and isn't really blowing cold air on the people when they're in the heating mode. Now, that's pretty complicated. Don't worry too much about that just on this one slide, but that's kind of an overview of heat pumps with W1 and W2. And again, the electric strip heat can be used as supplemental heat and also during the defrost cycle. Okay, now programmable thermostats are popular, these digital thermostats. Let me show you one. You have this nice here with this nice display and these buttons that you can play with and follow the manual, and then set the temperature and the time. And setback temperatures, the idea would be like this, you know, for a residence anyways, that you maybe want to maintain a certain temperature when people are home. Like you might cool, here's how we really think about it. We might say we're going to set it to be on auto, and we cool down to 73 degrees, and we heat up to 68 degrees, and maybe just between 68 and 72 or 3, we just ventilate. Okay, and that may be something, an acceptable temperature for people when they're occupying a building or a residence. But let's say people go to work during the middle of the day, Monday through Friday, and they're like, we don't really need to be running the air conditioning or the heating. Let's do a setback program in the thermostat, so we're changing those numbers so that we cool down, let's say, to 76 or 77, and then we heat up only to 64 degrees. So the system's really not hardly running when we're not home, but it doesn't get out of control, so that when we come home we can get the temperature where we want it pretty easily. So that's kind of the idea behind setback temperatures. And this idea of setback is actually pretty advanced, because even in very complicated large building energy management systems, we don't actually shut the systems on and off. We just rely on that setback so that we don't lose a building. And it might be that it's just like in the summertime when nobody's there, we put the cooling at 83 or 84 degrees, so the building can never get to 85. Because if a big building gets to 85 degrees, and then somebody says, hey, we need to come in, and we had a massive heat wave over the 4th of July weekend, nobody was here, the building got to be 85, 86, and then people show up on July 5th, even if you run the cooling all out, nobody's going to be comfortable or happy for at least half a day. So they do that setback where when nobody's there, they'll cool down to like 82 or 84, and when nobody's there, they'll heat up to like, 56 or 57 degrees. And in a sense, the system is off, but if you had radical temperatures in the building, also people can, when buildings aren't occupied, they're being cleaned, repairs are being made, so it keeps it somewhat comfortable for the workers. Okay, so that concept of setback is an important to understand. Okay, now communicating thermostats, again, now I'm going to talk a little more modern than this slide. With communicating thermostats in energy management, this is where you usually have a signal of 0 to 10 volts DC or 0 to 20 milliamps, and we use this communication signal. And a lot of times what we have on the wall, the actual definition isn't really a thermostat, it's just a temperature sensor that's reporting to a circuit board that makes the decisions whether to bring on more cooling or less cooling or whatever. So in these communicating thermostats, they're communicating as part of a bigger system. And also they might be, these larger energy management systems may be controlling the lighting, maybe controlling interior lighting, exterior lighting, other life and safety type of things, humidifiers. In Southern California, where this lecture is being made, we don't have a lot of use for humidifiers, but in some areas we do. And so maintaining the temperature. Also, in these communicating thermostats, a lot of times we'll be taking the outside air temperature and humidity along with looking at the inside temperature and then making decisions like, can we run economizer mode where for some reason if it's warmer inside and it's kind of cool outside, we can flush the building with outside air and not run the expensive compressors. That's called economizer mode. So we have different sensors, or we might say in the olden days, thermostats, to do these jobs. Now pressure switches, very extensive. I'll just give you the basics on this. The most common type of pressure switches would be a low pressure cutout here, and this is the electrical symbol for that, where if the system gets low on refrigerant and the low side pressure on the suction line gets too low, we don't want the system to run without refrigerant. The contact opens up, breaks the circuit as a safety, and the compressor is then protected. Similarly, the high pressure cutout would open up if the pressure on the high side got too hot, too high rather, and to protect the compressor and the system from failure, it will open up as a safety. And the most common reason that a high pressure cutout is going to be activated, open up, is a dirty condenser. Dirty condenser all day long will cause it to open up. The second most common reason would be a bad condenser fan motor, or condenser fan motor that's not running, perhaps because of a bad capacitor that serves that fan motor. So that would open up and save it. But there's other applications of pressure switches I want you to be aware of. On larger systems, we also can have a pressure switch that makes on a pressure rise, right, like this one is, and might be drawn normally open, and when the system runs here, if let's say you start with one compressor and one condenser fan running when you say bring on the cooling, that's what happens. But then if the head pressure rises, let's say to a pressure of 250 because it's kind of a warm day, then that closes and brings on a second condenser fan motor. And that 250, it could be any number, but it makes and breaks on a pressure rise to bring on a second condenser fan, a third, a fourth. There are some air-cooled chillers with 12 condenser fans on them. And we don't always need to run all 12, and sometimes we can get by with maybe 4. And so we can activate those based on the pressure. If it's warm outside, you're going to have a higher head pressure, or if the condenser's a bit dirty, you're going to have a higher head pressure. And this helps maintain a nice, constant head pressure with these pressure switches. There's other pressure switches too, which I'm not going to go into, but those are the by far most common ones that you're going to deal with. This is kind of a review, this slide, of what we're talking about. Again, it's These are generally safeties. On small residential systems, the high pressure cutout is by far the most common of the two. You'll have both of these on systems that are a little bit more expensive, or maybe in small commercial refrigeration you have both of these, or even on air conditioning systems over 5 tons you tend to have both of these in them. Okay. Now the differential, let's talk about that for just a minute so you understand. Here, let's go back to our illustration of it makes it 250, and if it were to break at 200, we would say the differential is 50 psig. 50 psig. So that's the differential. The cut in, 250. The cut out, or when we shut off that fan, 200 with a 50 psig differential. Okay, so those are very common pressure control terms. Okay, humidistats can control humidity, add humidity to the air, boil off some water, put it in the air. We can also set up systems where we run the cooling in order to drop moisture out of the air, because we know an evaporator coil is very cold. When air goes over it, the water condenses out of it. So in a sense, we can also have that as part of a way to dehumidify. Oil safety. Now all small compressors like this big and smaller work on the splash method of lubrication with oil inside the hermetically sealed compressors. All really big compressors like this big have a separate oil pump and usually oil heater that feeds it before it starts. But then the mid-sized compressors like semi-hermetics, sometimes they have built-in oil pumps that when the compressor turns, it has a little pump inside and it lubricates the internal parts. And since it's lubricating itself, the compressor, it'll give it 90 seconds to establish good oil pressure. And if it doesn't, then it says something's wrong, let's shut the system off. And then usually there's a manual reset button that a technician has to hit while they're troubleshooting in order to restart the system. We also have time delays. Now, back in the past, I used to install these little time delay relays on systems that would short cycle. People would fight over the thermostat or whatever. But almost all modern thermostats now have a delay on break and will not let the compressor restart for another 3 minutes. In fact, some of the very newest small thermostats for refrigerated boxes also has that technology now. Because one of my rules, like 10 commandments of air conditioning refrigeration, I should do that, is once our air conditioning refrigeration compressor stops, never restart it for 2 or 3 minutes in order to let the pressures equalize as much as possible. They almost rarely totally equalize, and to let the compressor and the windings cool down a little bit. Okay, so a lot of times that's built into the thermostats nowadays, and also the time clocks are built in also to the thermostats and or circuit boards. But we still use manual time clocks for things like freezers that have defrost timer motors that will bring on these big heaters to defrost the evaporator coils at certain times. Solenoid valves. Sometimes we use hot water or chilled water on large systems, and we have solenoid valves that open up or close in order to let the hot or chilled water flow in order to provide heating or cooling. Also on refrigeration only, we also sometimes have pump down systems where liquid line solenoid valves are energized, and quite often these are controlled with thermostats. And that concludes my lecture on pressure controls, thermostats, transformers, and other electrical components.